Um, and the program is all about batteries, the chemistry, safety, power measures, calculations, examples of products, and projects for ham radio components. So Paul, W9PEM, is an extra class. He's been licensed since 2001. He upgraded to general in 2018 and started exploring HF. Paul received his extra in 2023 and is mainly interested in digital modes of all flavors, antenna theory, design, and QRP radio. Dave is also an extra class amateur radio operator and has been licensed since 2018. He's currently active on VHF, UHF, DMR, operates mobile, bicycle mobile, wow, and portable QRP operations. Both are electrical engineers. Paul is also a field application engineer. Paul joins us by Zoom, and Dave is here in person. Gentlemen, you have the floor.
I will go ahead and start sharing. Thanks for the introduction. Let's just make sure that this is visible. Okay.
Yes, you're coming through fine.
All right. So thanks again, and sorry I couldn't be there in person. Had a scheduling conflict with some training. So I'm glad this will work out virtually. Dave and I know each other professionally, so I'm glad he's able to be there as a guest. And one minor announcement, Nate was going to be there in person. He had some kind of show and tell, but he got a flat tire just moments ago. So I don't think he's going to make it in person. I don't know if he's going to join via Zoom later, but he didn't say it, but I'll say it for him. He's sending his regrets. So I'll get started because there's quite a bit here, and I probably need to go a little quickly. So first off, I wanted to start with the agenda. Jean-Ann already covered this. Just go over basics, talk specifically about lithium batteries, talk specifically about a certain type of lithium battery chemistry, look into how we measure and estimate battery capacity and power calculations for use for radios, and then just talk about some examples of things that can be purchased and then some examples of projects that I and others have done. I do want to give an acknowledgement to a couple presentations that the club has seen before or is aware of. Jeff Whistler, W9KW, did a presentation that was shared with the club that was part of a Ham Radio Workbench podcast interview. So I included the link there. And then Peter, W0NG, did a presentation that was, again, adjacent, specifically about solar power, but definitely battery related. Jeff's presentation goes a lot more in depth into some technical aspects that I'm not covering. So there's a lot more information there for reference material for further reading. All right, so the battery basics area I think is a spot where some people will be real familiar with the terms and the concepts. Others may not, and so I just wanted to make sure I cover all the basics. When we talk about batteries, there's really two types, and the terms are primary and secondary. Primary batteries are good old AA batteries or some coin cells, lithium coin cells that are not rechargeable. And then secondary is the term they use for rechargeable batteries. These are lead acid, NiCad, nickel metal hydride, lithium. So those are just common terms in the industry for defining whether or not a battery can be recharged or used more than once. When we talk about batteries, and specifically with respect to rechargeable batteries, there's what's known as the nominal cell voltage. So this is when you hear about of cell voltage, it's really what they're referring to is what the voltage would be when it's kind of halfway between fully charged and where you shouldn't discharge it any further, which is called the cutoff voltage. Below that voltage, you really shouldn't try to draw any more current from the battery because it could damage it. So, some of the chemistries that we'll talk about, I'll mention nominal voltage, and you'll see, some are 3.6, some are 3.2. Like a AA battery is 1.5. So that's what that term refers to. The next two terms are probably the most critical when it talks about, estimating and characterizing and using a battery. So a battery is really a charge storage device. And the unit of charge, the standard unit of charge is a coulomb. But you never hear so many coulombs of charge when you hear batteries being rated. You're hearing amp hours. So an amp hour, in one way, you can think of it as how many amps you can draw from the battery in 1 hour. So if you have a 1 amp hour battery, you could technically draw 1 amp for 1 hour, or half an amp for 2 hours, or so on and so forth. But because it's really a charge storage device, when you look at it from the raw SI units, we're talking about coulombs. So 1 amp hour is 3,600 coulombs. I'd like to bring it back to the SI units. We often just use the term capacity for batteries. And then if you want to use that charge, then you need to understand how much energy and power the battery can deliver. So watt hours is a computation of the nominal voltage multiplied by the amp hours or capacity. And really in this, when you convert that, you're now talking about electrical energy, or in other words, how much power can be delivered over time. And again, bringing it back to standard units, a watt is a joule in 1 second. So a watt hour would be 3,600 joules, 60 times 60. And really, when you're asking the battery to do something for you, you're using it for some purpose, you're doing work. The battery is doing work, is the term. And work is defined as the transfer of energy. So battery holds charge, it delivers energy and power over time, and that's what the battery can do as far as how much work it can do. Then another term that's important when you're comparing different chemistries is depth of discharge. So this is how far you can discharge a battery safely, meaning safely as far as what's recommended by the chemistry or by the manufacturer. For example, lead acid batteries should never really be discharged more than 50%. So they have a 50% depth of discharge, whereas many lithium batteries can go all the way to 90% or more, depending on how the manufacturer specifies them. So they have more usable capacity than, let's say, a lead acid battery. The converse to depth of discharge, you'll see me talking about it later, is state of charge. So it's basically the opposite. If your depth of discharge is 50% and you've drawn it all the way down to there, then your state of charge is 50%. Cycle life, this is really the number of times a battery can be recharged until the capacity degrades to about 80% of what it was initially specified. So these are usually in hundreds or thousands of cycles, and different chemistries can support different numbers of cycle lives. And it all depends on how the battery is used and maintained. But once it gets below that 80%, that's where, the rating of cycle life starts kicking in. And then finally, load current. Current is just amps, but in battery terms, a lot of times you're seeing batteries rated with a C a number in C, like 1C, 2C, 10C. And the C refers to the capacity. And a 1C load current means that that battery can support 1 amp. Let's say it's a 1C. That means, and it's a 1 amp hour battery, it can do 1 amp. So if you got a 20 amp hour battery and it has a rated 1C load current, then it can deliver 20 amps. And that's kind of like an average. Sometimes peaks can be higher. You might see a battery rated for a 0.5C or 1C with peak to 2 or 4C, and that all depends on the chemistry. All right, I think
Power
got
tools,
through. Go ahead. Is there a question?
Yeah,
Or
no.
want to make a comment, Dave?
power tools are a lot higher, though. Sometimes they'll run at 3 or 4C, 3 or 4 times their capacity rating, because they're discharging them really quickly. But you can run them above the capacity. If you have like a 5 amp hour battery, you can discharge it at 10 amps. It won't be happy. You won't get great life out of it, but you can go above the C rating, is what I was just trying to say.
No, that's great. And Dave, jump in whenever. No,
Right,
I appreciate that. You mentioned power tools. If you think about like drones, those batteries that are used for drones, they could be in the 100C. The lithium polymer batteries can just have incredible load currents because those motors require a lot of power. I mean, you may get 20 minutes of runtime, but you're delivering, 20, 50, 100 amps when you need to. All right. I mentioned use the word battery and cell. I want to just make sure that was clear. These terms again. Cells are the individual units of energy storage. So when you think of a AA battery, it's really a single cell battery. Coin cell, again, single cell battery. When you start stacking cells in different configurations, then that is the battery. And then you can see this next slide. There's series and parallel combinations, or both. As you stack cells in series, the voltage increases, but the nominal cell capacity remains the same. So in this example, I've got some 3.6 volt nominal cells of 3,400 milliamp hours. I stack 4 in series. I'm now at 14.4 volts, but I'm still that 14.4 volt battery has a 3,400 milliamp capacity. And then the other way, putting them in parallel, we're maintaining the voltage, but now the capacity stacks. So now I have a 13.6 amp hour battery at 3.6 volts. As battery pack, and Dave can also attest to this, battery pack manufacturers will do both series and parallel to increase the voltage to the rate to the value they need, and then increase the capacity to get to, what's necessary. Like Dave, you want to make an example of like the golf cart battery?
Yeah, a golf cart battery, for example, is they're normally 48 volts, but they need to be about 5 kilowatt hours. So how do you do that? They're 20 or 30 cells in parallel. Now, the issue with cells in parallel, though, is in this example, they're all at 3.6 volts. If that happens, everything works. But if one is at 3.5, there's going to be current flowing in a direction you don't want. They're going to be flowing from the high one to the low one. So there's some practical limits on how many cells you can put in parallel. And it starts becoming advantageous to use more of them in series than parallel. And you have to go through some strategies to make sure that the cells stay in a parallel string I have the same voltage on them all the time.
Yep.
This is, wait, well, I'll just hold one up. This is a power tool battery from a company here in town that I worked on. It's a 80-volt battery. And there's like 4 in parallel in that one, and they're all stacked together. The battery management system is on top. It's got 5 microcontrollers in it. So it's a kind of a complex device. And Paul's going to talk about BMSs in a minute, I think.
Yep. All right. Thank you. You'll bring it up closer.
Yeah.
That
That's the power connector. It's got 1 microcontroller and then 1 for each parallel string of cells. The cells are all here. They have voltage. Whoops. They have voltage taps on the end. They're all spot welded together in construction.
Yeah, I think here coming up, you probably want to talk about the welding.
Yep.
All right, so lithium-ion batteries. Everyone loves lithium-ion batteries. They're light. They deliver good power. So I'm not going to go into electrochemistry too much. Just wanted to show, what happens within a lithium-ion battery. Typically, you've got a graphite anode, and then the cathode. When you talk about different lithium-ion chemistries, it usually refers to the cathode material. When you charge a lithium-ion battery, you're shuttling charge from the cathode to the anode. And then when you're discharging, you're shuttling charge from the anode to cathode. The term charge, like charging, there's the reason why it's called charging, because you are affecting the movement of charged ions between the 2 sides of the battery. And then there's a little periodic table there, illustrating the fact that lithium is the lightest of metals. That is one of the main reasons why a lithium battery is quite a bit lighter than, say, a lead battery. It's got many fewer protons. All right. So then talking about different cell types, there's different constructions that can be done with the lithium cells. A common one is called cylindrical, and a lot of tools, and I don't know what size in that pack you had, Dave, but in this example, an 18650 is a common cylindrical cell size, 18 millimeter diameter, 65 is 65 millimeter height. And these cylindrical cells are created in what's called a jelly roll construction. You can almost think of it kind of like how if you know how electrolytic capacitor is made with sheets of material that are rolled up, similar. And it's basically you can see the construction there, how the cylindrical cells are constructed. And then another type is called prismatic. So prismatic is likely what we're all more familiar with, being that's what's in cell phones, because you can make them flat, rectangular, long, and they still have the separation in the same layers, but you can create them in more, flat and rectangular shapes. There's advantages and disadvantages to each. I wasn't going to go too much into that. But Dave, I was going to ask, what size cells are in that battery pack?
They're 18650s, and
Okay.
that's probably the most common size cylindrical cell you will see. They use them in everything from power tools and laptop computers up through, the first generation Teslas had those in.
Yeah, I think the new Teslas have a slightly larger size now.
21700s, which are it's 21 millimeters and 700 millimeters long. And a lot of the power tool vendors are going that. We're actually seeing in the market 18650s are going to get cheap as people switch to 21700s. So there's a opportunity there if you're into building stuff with them right now.
Okay. All right, Dave, you want to talk to this one?
Sure. Of course, well, first of all, I'm honored to say I'm an engineer, but I have a degree in physics, and a physicist means that I like to blow things up once in a while. And I've been involved in a few things where we had some incidents. And I started asking, and I have a son who's a PhD in chemical engineering, and we talked a lot about what's happening inside of a battery. And because at one of the jobs I was at, they had an incident. There was a fire, and I didn't have to handle the fire, but I was unprepared to understand how to deal with a fire. And I built some batteries at home, and I developed some rules of thumb that I want people to understand, because if you understand what's going on when you have one of these events, it's not necessarily scary, right? It doesn't have to be. And if you don't know what's going on, it's very scary, right? Because you don't know what to do with it. First of all, there's a myth that says there's enough lithium in these batteries. If you throw it in water, lithium reacts with water. We've all seen those pictures in chemistry. Well, these lithium ions are locked up for the most part in other compounds, and they don't react catastrophically like that. But it is an exothermic, a thermal runaway reaction. And your goal is to keep it cool till that particular cell is discharged. And if you can keep that cell cool, I'm going to hold this up as a model here. For example, let's say that, I got to get closer. One of these cells overheats, let's say the one on the end, and I got to hold up so you see it. On one that sense, overheats and begins to vent. If you can keep this pack cool enough, you can prevent all the other ones that going off, having a cascaded failure. But they fail in different ways. Some of them just smoke a little bit. Some of them flare up. Some of them, they don't really burn. I mean, the definition of burning, what I think burning, they really don't do. And by the way, I'm not a firefighter either. I just had a bunch of fire extinguisher training in industry and been through some of these. But yeah, but the strategy is really simple, just as it's there. Don't overcharge them. Keep a bucket of water handy, because if they go off in a thermal runaway, dousing them in the water is the right thing to do. Keep a fire extinguisher nearby, because there's a 700-degree F jet of a plasma or gas coming out of that thing that will start everything around it on fire. So the fire extinguisher is for the secondary fire that's created by that. And yeah, and all kinds of things can cause a failure. If you look back at, Paul, can you back up one slide just for a second? So, yeah, that one. So these things are a jelly roll. So if you drive a screw through one of the cells on a cylindrical cell, it'll start a fire. If you drop it too hard and bend the can, it'll start a fire, start a thermal runaway. So there's lots of ways they can fail. Sorry, Paul, you can go ahead on that. That's it. Keep it cool, let it discharge, then get it out of the water, because you don't want to leave it in there for a long time, because the electrolyte can leach out and make some bad chemicals. Don't drop it. Don't run a screw through it. There's a lot of people who are in the battery business who have taken a battery pack like this apart, and this is assembled with long screws and short screws. And guess what happens? They put the long screws in where the short screw should go. They drill through the side and go on fire. Another one we had was at my current job is a mechanical contractor was there, and one guy was holding a piece of sheet metal back with the back of his drill, and the other guy was driving a sheet metal screw through it, went right in the battery pack. So these things aren't, people make them out to be really, really dangerous. They're not. They'll go into thermal runaway. If you control the heat, you are going to come out with a pretty positive situation. So jump to the next slide, please. So there isn't much, as I said this before, there isn't much lithium in them. They're not going to go crazy if when you dunk them in water. Get them underwater, keep them cool, let the cell discharge, and control the secondary fire. But don't leave it in there because nasty compounds will leach out from the electrolyte. And then when you get it out, you're best to hook up a light bulb to all the other ones and discharge the cells and then dispose of it. But that's an example of one where it had a pretty bad discharge, and you can see the place where it ruptured, and that's where the gas jet was coming out. But they've done a pretty good job of preventing the other ones to do it. Taking the battery out of the circuit won't stop it. Dousing all kinds of water out won't stop it. Burying it in dirt or something else to remove the oxygen won't stop it. It'll continue to run until that cell is discharged. So it's just something to keep in mind. But it's not that, again, it's over in 15 minutes. When I work on batteries in the garage, and I've built a few of them, I get the car out of the garage, I put it on a table, I have a bucket of water next to me, some heavy gloves, and I had one time where I had a problem. I just knocked the battery into the bucket of water and everything was good. Not an event at all.
One thing I wanted you to touch on, Dave, these, I don't know if you can see my mouse, but, oh
yeah,
maybe uneducated people on battery construction may think you can solder the tabs, if you want to talk about that.
Yeah. So if you look at a battery drawing, there's two parts to it. Can you go right there? If you look at the top, there's which I always get them wrong, but the positive side, which is the anode, right? Yeah, is a little cap, and there's actually a pressure release valve in it. So if that thing starts to go into thermal runaway, that'll open up to take it out of the circuit. But the rest of the pack, rest of the cell it's a bucket. It's a like the bottom of a beer can. And if you're going to get solder to flow out, you have to heat that entire thing up enough for solder to get out. So every person who's really good at building circuits says, oh, I can solder to that battery. And the answer is you can't. If you don't get it into a thermal runaway situation, you're going to take so much life out of that battery that's not worth it. You can get a small spot welder. I was going to bring one from Amazon for like $30. And you can use that, and that'll work awesome. Or borrow one from someone. They work really, really well for that. But don't try to solder them. If they have tabs on it, you can solder to the tabs. That works great. But don't even try to solder to them, no matter what the internet says. You'll probably not have a positive outcome, is what I really wanted to say. But also, there's they call them what do they call them? A PTC device on top, which is some people say it's a positive temperature coefficient. And it'll just pop the top of the cell off to get it out of the circuit.
Electrically out of the circuit, right?
Electrically out of the circuit, yeah.
Okay. Yeah, just because it looks like there's solder, but that's not solder.
They're not soldered. No, they're strips of stainless steel or nickel that if you build them at home, you use strips of nickel and you'll spot weld them together. And have that spot welder around in your electronics lab is actually pretty handy. I've used it for more than just building batteries. If you have like a radio with a coin cell in it, it's a great way to tack those in place too. So it gets used for more than just building batteries, at least on my bench.
All right, I'm going to continue on here. So
thanks, Paul.
Yeah, no, great. I alluded to some different chemistries. I'll just kind of touch on this briefly, and I kind of made bold the kind of like some of the key things. The two most popular ones that we talk about are cobalt and phosphate. Cobalt is really what is probably most ubiquitous. Cell phone batteries are cobalt chemistries, and that was referring to, again, the different cathode material, I think it was. They're good because they have a lot of specific energy, and I have some definitions on the side there. Some that I've covered. Specific energy is really about density. How much energy is in it per kilogram in this case. So, if you want the most bang for your buck as far as energy storage, then the cobalt batteries are the ones that have it. And that's why these are for cell phones. You get the longest runtime. The downside is that, their cycle life isn't as great as some others. Probably everyone can attest that after a couple of years of recharging a cell phone that doesn't hold the charge very well, you're going from like, a day and a half or 2 days of cell phone to like, a day or less, and you're always recharging it. You've kind of gone past that depth of discharge. I mentioned manganese. That's kind of like a little in between, between cobalt and phosphate. The key characteristics there, it can have a little bit better peak load current. You can draw from it. I think, Dave, manganese is some of those chemistries commonly used in power tools sometimes.
Right. And everybody, they work with a battery vendor or a cell manufacturer, and they might change the chemistry a little bit so they can get specific characteristics. But the reason they use a power tool is a pretty tough application for a battery because it can't weigh a lot. So that means that it's going to be heavily loaded when you're using it, right? It's going to be, it's not like a UPS. You don't want it to run for 30 hours. You want to take those bolts off your tire or cut that wood or whatever you're doing with it. And you don't want to carry around all that extra weight. So power tool is actually a really tough application for batteries. And that's why for example, that peak load current is 10 times its rating. And cobalt, you can go a little higher than 2C. I've seen it, but some of them, there's some mixtures of manganese. If you think about it, on the left-hand side, we would talk about those as a power cell, and the ones on the right-hand side, well, the phosphate ones is peak load, but they're more what we call an energy cell. They're more for longer term, lighter loads for over longer periods, right?
Yep. So I am going to focus on the phosphate ones. In particular, what's kind of convenient, I'll call it, for the nominal voltage of phosphates cells is that you can stack 4 in series and you get about the same voltage as a lead acid that is 6 cells in series. So, if a phosphate battery is designed appropriately, it could potentially be used as a drop-in replacement for lead acid. Again, you don't necessarily always want to assume that, but the benefits though versus lead acid, you've got much lighter because it has higher specific energy, more cycle life, especially if properly is maintained. You can recharge it more often, or many more times. It can potentially have much faster charging. We all know it takes a long time to charge a lead acid battery. And then again, discharge currents can be high, but really to have it well maintained, you want to kind of keep it to 0.5 to 1C. You don't want to, really try to drain the life out of it, with a heavy load. On the cons, or something to consider, lithium ion in general cannot charge below freezing. That will, really degrade or damage the battery if you try to charge below freezing.
Because you'll get metallic plating of the cells, and that makes it unsafe to recharge again. So
yeah. So don't even, some people say 34. Don't go below 34F. Because of the chemistries and for safety, cells or battery packs must have protection circuitry because you don't want to have a thermal runaway. It is more expensive, but on the flip side, it lasts longer. You may replace the battery less. And then because this is kind of like where everyone is very focused on lately, your mileage may vary with suppliers. You really have to do some research because everyone wants to make lithium iron phosphate batteries. So, you got to see what's out there on the market. There might be some lower cost options, but then, is the quality there? So when it comes to charging, there's essentially for lithium ion, you basically have, I've listed a 4-step process here, but it boils down to 2 steps: a constant current and then a constant voltage. So there's a constant current. Usually, in this case, you can see from the chart here, it's a C/2 charge current. So if this is a 40 amp hour battery, you're charging it at 20 amps. And then once it's got to a certain cell voltage, in this case, usually that's around, between 14.4 to 14.6, really max 14.6, then you're switching to a constant voltage. Unlike lead acid, you don't really need to float them because they don't have a high self-discharge. And like I said, some cases, some packs can be used with lead acid chargers, but really it's best to use the proper charger for the voltage and chemistry of your battery. Then on the other side, discharge, the key takeaway I want to show here is that, like with any battery, the lower the discharge rate, meaning how much current you're trying to draw from it, will generally have higher battery voltage versus heavier loads will pull down the battery voltage. And then that has to do with the internal impedance or resistance, which changes as the battery ages, and it changes with temperature. So I've got some typical voltages. You've got, is it a light load? So again, I'm using that 40 amp hours. So now here, 40 divided by 5, I'm drawing 8 amps. Fully charged, you're at about 13.3. At that 50% rate, 50% state, you're at about 13 volts. And then when you're essentially fully discharged, you're down right, near 12 volts. And I see from the chart there, once you get past that 90% rate, it's a cliff. So my big takeaway here is that just doing a voltage measurement on your battery may not tell you where you're at. You'd have to know, your load, your temperature, condition of the battery. So just doing that either open circuit or under load voltage measurement may not give you a good, feel for where you're at in that depth in that state of charge.
Let me add something that quick.
Mhm.
Yeah, you notice that's very flat. So it's really, really important if you're driving your Tesla or you're driving screws with your drill to know how much juice is left in your pack. So they use a variety of methods to do that. If you can get a precise measurement of the terminal voltage after the battery has rested, that works pretty good. But most cases, they measure the current over time. They integrate the current that's going out and they integrate the current that's going in. And then they have a correction that comes in when the battery's been sitting. But you can't really look at the terminal voltage and get a really good idea, what your usage is, especially if you have something that's with a wild duty cycle like a vehicle or a drill or something like that. It's very tough. You have to use a more advanced method.
Yep, and good segue, Dave. So wanted to just kind of recap real quick about amp hour and watt hour again. So, how do we measure and how do we know or compute how much of the battery we're using? So because batteries are rated generally in amp hours, if you know exactly how many amps you're using at any moment or an average, if you have an average, then it's easy. You just, divide that out to get how much, potential runtime you have in hours. Whereas watt hours, if you can calculate the number of watts and you know how many watt hours of energy your battery has, then it's just a subtraction. You're just deducting the watts from the watt hours, and it's a little bit easier. Here are two examples of batteries where they rate their watt hours slightly different, which is, I found that interesting. The different manufacturers will have different nominal voltages, even though they're the same chemistry. The LI Time one has that 12.8 nominal voltage to compute the watt hour, but the Bioenno has a 12-volt nominal voltage that they use to calculate the watt-hour rating. So essentially, the Bio-NO1 is being more conservative. You've got maybe a little bit of reserve in your fuel tank there, because they're kind of underrating.
Yeah, they do that. They're playing a few games with that. So if you run the battery, I'll say in the middle of its range, you'll get more cycle life out of it. So you're trading, I'll say, amp performance versus cycle life sometimes by the way they're rating the battery.
Yep.
And you have to watch out for that. Um,
So Dave mentioned BMS. So, more advanced lithium batteries and packs will use battery management systems. So besides safety, these are monitoring all sorts of parameters: voltage, current, temperature, state of charge. It's also ensuring that it's being charged and discharged safely. And some BMS systems will expose the data. There's a protocol called SM bus. It's kind of like a I squared C, that can be used to read it off. Another way, if you can't tap into that BMS, is to use a shunt current meter. This is an example of one that I've got a little pack that I made. Basically, you've got and I'll talk about more in the next slide, a precision resistor that you're simply measuring the voltage drop across a very low value resistor to compute the current. And this is that display and that shunt, was a very inexpensive thing I got, but it was nice to be able to show instantaneously, voltage, current, power, and energy over time. So just talking briefly about shunt meters. Again, you're putting the entire load current through a precision low value high current resistor, and then you're measuring the voltage drop. It's simply Ohm's law. So the output voltage, in this case, I'm showing an example of using an amplifier to amplify the small voltage drop, at 100 amps with a 0.5 milliohm shunt, that's only 50 millivolts of voltage drop. So typically some current sense amplifier is leveraged in there. They come in different sizes and form factors. In this graphic, I'm showing a company called Victron Energy. This is a smart shunt that's got Bluetooth interface. I use this on my camper. And the bottom left shows a little snip from the app, showing instantaneous battery voltage, instantaneous current, how much amp hours have been consumed, and then estimating the state of charge.
Can I add that quick, just a minute, just quickly? One thing to watch out for is if you have a shunt meter, they work great. However, they will have a finite range that you can measure it at. For example, on Paul's camper, if he plugged his iPhone into it, he might not see it on that meter because it's just down in the weeds in terms of that. And that's been a problem in industrial applications. Someone will have a big battery like in their golf cart or on a power tool, and they try to plug their cell phone into it. The BMS can't tell because the current is too low. So you have to use some other strategies for really light loads. The shunt meters work great for the peak loads. They don't always work so well when the load is really, really small compared to the capacity.
Yeah. So I just want to kind of talk a bit about a project I was doing where I have a battery pack that exposes that BMS data. I created a little gadget that read the data. So I opened one up and saw which part it uses this Texas Instruments gas gauge. Kind of reverse engineered some things, looked up the data protocol, figured out where the connection pins were, and then created this little widget that basically asks the battery management system for the value. So in this case, I'm not using any shunt meter or anything. I'm just leveraging the data the battery is already doing for itself to keep track of its own parameters. So I got voltage, current, number of cycles, which I think was the most important thing for me to know how many cycles a used battery had. And then it even goes down to individual cell voltages. So just wanted to just kind of expand on this real quick as what I felt was a neat project. I shared that information with the ham radio community, and another ham took my code and port it to a device, and they can see that same data on a website, on a web page. They could, keep track of it, on a cell phone, connecting to the website. But there's a lot of data that the pack manufacturers can provide beyond just, maybe what normal people care about with just, what's the state of charge. And then finally, another ham took my little gadget design, shrunk it down even more to just a little display that sits within the battery pack. So I thought that was really cool. And then, this is, I think, one of the things I like about, the hobby is that where there's experimentation that can be done in many different aspects. And I think it's cool when people share what they're doing and build off of it, and kind of leverage the experimentation side of the hobby. Okay, so I'm trying to go a little quick so I can be conscious of time. So moving into the radio side now, finally getting into really ham radio. I scoured the internet and people testing radios and manufacturer data and QST, articles, and I tried to put together a view of like what are some common portable radios that would be used with batteries. So here's a chart for that, and again, these are not scientific, numbers. Your mileage may vary. I took some liberties with rounding, but I wanted to do a general comparison. Your favorite radio may not be on the chart, but just kind of showing, there's a survey I found, what are the top, portable radios. So I included those on the chart here. And then when it comes to, using this information to estimate how big of a battery you need for a certain activation, let's say, mode makes a big difference because the duty cycle is much different whether you're FM or digital, which is always 100%. CW, usually 44% or less. And then single sideband voice, you're at 20% or so. And I got those duty factors from this link here, from this really great article, a presentation. Would recommend reading that. That talks about more in depth about operating on battery. So I'm going to go to the next one. I used the example of the IC 7200. That's a radio that Nate likes to use for Parks on the Air. I put a link to the spreadsheet that's shown here in the slide. I plugged in what he usually does, which is he likes to run with, I guess, 100 watts. So it's 20 amp during transmit. In receive, it's like 1.2 amps. And then if he's doing voice, it's about a 0.2 duty cycle. So then, and he said he's keying up, half the time. He's doing a 50-50 receive transmit duty cycle. So the way then the calculator works, you'd say how many hours of operation you want to run. So in this case, 2 hours. So then finally it comes out saying for a lead acid battery, which has, again, about 50% available for the depth of discharge, you need a 10.4 minimum amp hour battery to do this 2-hour activation with that sort of parameters. Or with a lithium iron phosphate battery, being able to discharge it down to 90%, you would need a 5.8 min amp hour battery. Again, like I was showing with the other examples, you got to pay attention because, like I said, some manufacturers rate their amp hour and watt hour differently. So it is important to know what your current draw is at your operating voltage. And, again, even better reason to have some way of monitoring the power with a shunt meter or some other tool. So going into batteries and some of those tools, just this is a quick, again, if your favorite battery manufacturers not on this list, I apologize. I tried to just keep it short. Bioenno, the club gives away those batteries during raffles. They're well known in the ham radio community. They come with power pole connectors, very convenient, small, compact. There are some conversations on the Groups IO about good other battery pack manufacturers, and LI Time came up as well recommended. I guess the independent testing shows they do live up to their capacity rating. Dakota Lithium is one I see a lot, both in advertisements and then just they have a lot of sizes that you could choose from. They are, I think, generally made in the US, and they have a real long warranty, which is nice. And then finally, the Renogy ones are typically larger capacities and are more for like home energy storage or, campers or that sort of thing. And I kind of showed examples from what I pulled from when I put the presentation together, what sort of the price ranges are. I didn't put a table for like price per watt hour, but just to give you an example of like, they're not that expensive, especially considering that if you treat them well, they last a long time. Instead of buying new, you could always buy some used. I've been buying used batteries from someone that recycles them out of medical equipment. The nice thing about that is depending on where they were used in, they could be well maintained and they could have pretty low cycle counts like that. You saw in my gadget, it had about 1,200 cycles. Now in a cobalt chemistry, that's probably, pretty well spent past its, prime. But if it's being well maintained in, let's say a hospital setting, then, that might be only halfway through its usable life. So, they can come quite discounted. The cons is, you got to really, know your supplier or know what you're looking at. Like I found this one on eBay. Good. It was a cheap price, but in this case, same amp hour rating, same voltage, but this came pre-wired with only 14 gauge wire. So it's only usable for 15 amps. Whereas the other one with big M10 or whatever it was terminals, you can do 20 plus amps out of it. So, again, I like to use the term your mileage may vary with used batteries, but it is an option. There's a lot of vendors out there. A lot of people are recycling batteries out of things. Again, wanted to mention some projects. Nate didn't get a chance to bring this power box that I built, but I see a lot of people in the community taking a battery, sticking it in a box. I don't know if Fred brought what he had talked to me about. Maybe he brought something. But just I was having these batteries laying around and I wanted to make it more convenient to use. So tossed in an ammo box, put some switches and connectors and USB charger, just made it more convenient. So the one guy that I KF0LMH down in Missouri, he's the one that I get a lot of my used batteries from, and he recycles them out of medical equipment. He has a lot of batteries to choose from for himself and for his club. So he's been making for his club just a massive battery array. And here is showing a 26 kilowatt hour battery system. They're running their full field day just on batteries, no generator noise or anything. So little crazy. Probably won't see that in many clubs, but he's got the batteries, so he put together something crazy.
Just a point of
Um,
reference, like a golf cart takes about a 6 to 8 kilowatt hour battery. So, and they can run that around the golf course all day. So that's a point of reference. That's pretty big.
Yeah. Yeah.
I'm really concerned about matching cells when you're building something that big, but that's pretty big.
Yeah. Um, for Parks on the Air and some like Go kits, a lot of people, are, combining the batteries, radios in a easy to grab and go bag or box. I see a lot of times with Pelican cases. And then this the last example with solar charging, inverter, a battery on a hand cart. I believe the club has one of these or something similar that I remember seeing last field day. Someone can correct me if I'm wrong or go further, but I thought I remember seeing something like that. But this is an example of another project. My point for showing this is like, what are some of the things you could do from a building and experiment? I like to build things and design things, so these are sort of things that get me really interested, even though there's like only one radio shown in this whole picture. Well, I guess there's some in this box here. So I think wrapping up here, again, some other accessories, watt meters, I think are gonna, for someone's running on battery, one of your best friends is some sort of watt meter so you can keep track of, how much power you're using. Many manufacturers make one that looks just like this. PowerWorks is just one that I think people are familiar with from the Anderson power poles. If Fred did bring his box, I believe his box has one of these Epic power gates. So this could be used for a battery backup system for your radio, automatically switching over between mains, power, and battery. And then the Super Booster and the MFJ parts. This whole time we've been talking about batteries, 12.8 nominal, 13.3 fully charged when being used. But we all know that, the radio manufacturers are all speccing everything at 13.8 because that's where you get, your full final amplifier power output. So these devices will take your battery regardless of the actual voltage, sometimes down to 10 volts. You can drain the battery, all the way and will boost it to that 13.8. And, you're not really getting more, you can't get more energy out of the battery. It is what it is, but you might get more max power for your radio by boosting that voltage up to 13.8. If that every watt counts, if you really want 100 watts out of the 100-watt radio versus, if you're running your 100-watt radio at 12.9 volts, what is the actual final wattage output? I'm not sure. And then finally, again, I see these a lot in the market now, these power stations. These are kind of, very consumer friendly, all in one. Some take solar panels directly in. They have built-in inverters they're basically a mini generator, but using lithium batteries. And I think that's my whole thing. So again, thanks for listening. Hopefully I didn't go too long and, keep experimenting. I think that's one thing, part of the hobby. I don't get on the air too much, but I do like experimenting. So thanks.
Oh, I got a show and tell. If you
Yeah, go ahead. I'll leave this slide up.
I'm gonna probably won't look so good online, but this is a battery that Briggs and Stratton is making now for light industrial, I don't know, chore batteries for things like maybe rototillers or cement mixers or things like that. It's a 1.5 kilowatt hour, 48 volt battery pack. And it just shows you what you can do with it. These are 18650 cells in it. It weighs about 25 pounds. And we've just released this, so it's available everywhere. It's got what's different about this than like a power tool battery pack is the interface is kind of open source. So you can build your own devices for it. We have this thing here with an inverter. I don't know if you can get the camera down to see this. We have an inverter on it just as a test device. And also every test system needs a test light, right? So we have a test light that we got off of a lighting tower that we also make. And I just wanted to show you that. And that's also the biggest, ham guys love Anderson power poles, right? Paul, I know you're down at the Molex thing, but this is an Anderson connector. Ham guys love that.
Paul, stop your share.
No problem. I will stop that and I will go on mute.
No, I have to find it. But it's interesting to see how much light this will do. We put why am I not finding that thing? Well, there it is. We put this one of the companies we work with puts with 4 or 5 of those batteries on in a lighting tower like you see along the road. And let's turn this thing on. There you go. So everybody likes a test light, right? But that's quite a bright one. And on the back of this thing is a power inverter. We've had employees when they've had power outage, they run into the office, they grab this thing, they run the refrigerator off it. This is right out of a RV system. So they're not that expensive. We just built this thing in our shop for a test unit, but it gives you the idea of some of the things you can do. And I would consider looking at some of the batteries that are in the 40-volt range for portable operation and get a buck converter that would knock it down to your 13.8, because then you're working on the positive side of the battery. I think you'll get great performance out of it that way. But again, yeah, this is what I work on. Designing the BMS, writing the software in it, figuring out how to charge them, figuring out how to make them operate in parallel. And I'm going to start using a much smaller one of those in field day. I have some that I built myself.
All right. Thanks, Dave. Well, I guess I'll hand it back
Yes.
over to you, Jeanette.
I've been working with, experimenting with the Ryobis and the Milwaukees. And this second here. There, duck season. And I've been experimenting with bucks and all that. It's pretty promising what we can do with this stuff from small size up to big. And it's been working good. And you want to, especially a buck converter, select the higher quality one. There's a lot of knockoffs on Amazon you may want to be careful with, because when a buck fails, it's gonna feel short. It's gonna put the full voltage out. So stick with the higher quality brands of bucks. That one display is a D-Rock display. Show up the amp art, actually works really good. That is an Amazon. D-Rock seems to have some pretty decent build quality. I've been very successful with them. Very happy with them from Amazon. But for the bucks, I'd be very careful.
Thank you.
Batteries. This is a power tool battery, but it's completely unusable for a non-power tool application because it's got its own disconnect FETs on it. And you have to send it some kind of encrypted code to tell it to work. And the conventional ones from Ryobi and Milwaukee don't have that yet, but you also don't have any, like our batteries here have I'll say over discharge protection, and they'll shut themselves off. So you don't cook the battery because you've discharged it too deeply. If you do your own, be sure you have a BMS that will protect the battery from too deep of a discharge, or you left your radio on and fell asleep, right? And you cook the battery because you over discharge it. But yeah, power tool batteries work great too.
Are there any questions or comments in the room? Okay, we have one so far. Gary Sutcliffe.
Yeah, thanks. Talk about building batteries. I've watched some YouTube videos on it, and I appreciate you go into the safety aspects, which I haven't seen in some of the YouTube things. But my question is, can you really save any money, or what's the advantage if I just want a 12-volt to run a radio portable? Can I save money by building my own battery pack?
I would say no. Now here's why you want to build your own battery pack. If you can get them really cheaply, or you need a specific form factor, then I would build one. And that's why I was doing it. I had a supply of them, 18650s that I got. I wanted to learn how to do it, so I did it. But if you're not concerned about the form factor, you might just as well go buy one. Just make sure it's got a BMS in it and you have the right charger for it.
I have another question too. Working on a project the last week outside and using portable electric drill. And I had a couple of battery packs. Do you have any recommendations? Like just don't use a battery pack till it stops running, then swap the other one in, or is there some?
I think if you get more cycle life out of them if you do not take them to the limit. So, and I've seen a lot of ones come back where guys in the trades have really, they have 2,000 or 3,000 cycles on them. They don't last very long, but they keep switching them out of the chargers. I would say is don't, there's a wives' tale that says, like the old NiCads, they said you got to discharge them all the way. With lithium ones, you don't want to discharge them all the way. And also you don't want to store them fully charged over the winter either. That's another thing that a lot of people don't get. But read the manual for your battery. It'll tell you how to do it.
Okay, thank you.
We've got one more question.
I guess the comment, if you're going to build something with 18650s, you can buy both protected and unprotected
Yeah.
individual cells. And you might want to consider the protected ones if you don't have a more sophisticated BMS.
Thank you.
Yeah, but the protected ones, so a good BMS you could put almost any power supply on it, and well, not any, but and the BMS will control the charge. Like on this battery here, the bigger industrial ones, the BMS runs the charger. It tells it how much current to put out. It completely controls the situation. The less expensive ones, they have a switch in it to prevent you to do it. The protected ones, I think they're more catastrophic, failures. They don't really control the charge. The real advantage of a BMS is it'll prevent you from over voltaging it or over discharging the battery pack, as well as over temperaturing it.
Okay, very good. One more question in the room.
You see these chargers like on Amazon and stuff, and maybe you have some batteries and there'll be different amperage on the charger. Do you have a problem like if you have a 12 amp battery, if you put a 20 amp charger on there?
I have to see the specifics, really. Like all the bigger ones we've done is the battery runs the charger, or I program the charger not more than like 0.8 C for the cell. Like for my RC systems, my radio control ones that I use, even the 18650s that I use in the radio control transmitters, I never charge them at more than half the 0.8 C. So I am the battery management system in that case, to prevent it from overcharging. I would not charge anything more than, like 0.75 C.
Yeah, I think one C is, you're really pushing it, and then in that case, you're
It
over
doesn't know
one
anything
C.
about battery. It doesn't know anything about the battery at all. It just
Right.
knows the terminal voltage. Most lithium ones will do a constant current up to a point, and then they'll transition to a constant voltage. Well, it's called CCCV, so it'll go constant current and up to a constant voltage until you get to full charge. No, but you can cook a little battery on a charger with I've done it. It's not.
I always thought the battery would, as it's building up current from being charging, the battery charger backs off. Like maintains it then after a while.
It
smart
will.
chargers
It depends. Like a lot of the cells, the smart batteries and smart chargers, and you're seeing them more and more everywhere where they've got their BMS in it. They will shut the charger down and keep you from overcharging it. But if you just have like the RC packs, no, they won't. The batteries will just heat up. They'll heat up enough that they'll go into thermal runaway or cause it some damage. If you try to zap it like with 2 C, for example, of a charge rate.
I know some of those polymer batteries, they sell those charging bags, those like fireproof bags that, because some people want to like charge them real fast or
Yeah, I mean, don't abuse your batteries. They'll last a long time. I guess I'll say that. But the charge proof bags will control that jet, but I don't know. I just follow the same things. Just keep out in the open air. If you're working on the battery, have water around to dunk it in to keep it cool. And you'll be okay. It's less dangerous than a can of gas.
Very well. Do we have any questions or comments from the Zoom audience?
Yes, Jeanette, I have one. This is W9MXQ.
Go ahead.
Okay, well, first of all, thanks to Paul and Dave for a great presentation tonight. Extremely interesting. I just have one quick question on something you said, Paul, and maybe you reiterated, Dave, not sure. But the rating for watt hours or ampere hours, I should say, on a battery, you talked about the idea that like a lead acid was intended to be discharged to 50%, whereas a lithium ion might be go to 80%. Is the rating that's given, like a 100 ampere hour battery, does that consider that fact, or is it all assuming complete discharge?
yeah, so if that's a great question. So 100 amp hour 100 amp hours lead acid battery should only be used down to what it would amount to 50 amp hours. So yeah, that's a great question because you get a 100 amp hour lithium battery and you're getting 90 amp hours worth of charge, energy out of it. So that's something when I was looking at batteries for my camper, I could get some, less expensive lead acid batteries, but I'd basically have to buy double the amount of amp hours to get the same amount of useful or recommended useful charge out of it.
Okay, that's been my hardest thing over the years in using batteries to really determine exactly what my capacity is going to be. Anyway, I'm sorry, I interrupted you.
One other thing to note is a lot of these guys, especially with lead acid ones, it's not at the 1C rate when they say it's 100 amp hours. That's not 100 amp hours. That's not 100 amps for an hour. That's 10 amps for 10 hours. They'll do it like
Okay.
it might be that might be the rating at the 10-hour rate, not at the 1-hour rate. Especially on lead acid ones that build up internal resistance when they're discharging quickly. So you got to read the fine print to see what the rate it's based on, as well as because it's not a complete comparison, right? If it's 100 amp hour battery pack, you might not be able to get 100 amps for an hour. You might be able to get only 80 amps for like 30 minutes at that high rate. But if you do it at 10 amps, you'll get 10 hours worth of, you got to read the fine print.
Okay, well, thank you very much. That's been a real mystery in
Got
trying
another
to use
comment.
batteries for temporary service. Thank you.
Bill, we've got another comment here, but we'll come back to Zoom in a second.
On lead acid cells, it depends on the construction. And it's typically like an automotive type battery it'll give you, there'll be different ratings. You'll get a 20-hour rating, which for a 100 amp hour battery, that would be 5 amps for 20 hours. At a 1-hour rating of that very same battery, it's only 50% efficient typically. So you could only get, let's say, 50 amps for 1 hour. Now, then you can terminate the discharge, let the battery rest, and at a lower discharge rate, you can remove the balance of 50 amp hours. But it's all a function of the discharge rate. So when you get a lead acid battery, what you'll want to do is get the data sheet that will show you the discharge time at the various discharge rates, current rates. But like I say, you'll have a cutoff voltage, and if you cut off at, let's say, a higher discharge rate, and then you wait, it will give time for the electrolyte to equilibrate, it remix and penetrate the plates, which would be pasted plates that we're talking about. And then you can get at a low discharge rate the balance of the 50 amp hours out of it. So it's totally a function of the discharge rate. The automotive types will also give you a cold cranking current, and that will be at a very high discharge rate, what is the max that you can get out of it, but that doesn't mean it's discharged. So you have to look at the data sheet for the type of battery. Like cylindrical cells that are AGM and lead acid can give you a much higher discharge rate than will, say, a liquid electrolyte or a flat plate AGM cell. The cylindrical gives you much higher discharge rates.
Okay, very good. We're running a little behind tonight, so are there any other questions from the Zoom participants? Well, hearing none, thank you very much, Paul. Thank you, Dave. Very informative, very well laid out. Wow. Great presentation. Thank you so much.